Today we're going to talk about first order linear differential equations, and we will actually be doing a bunch of integrals solving for these differential equations. So we started to do that when we were doing separable differential equations. We separated it and then we do what we've done before. So this, I guess, would be the first kind of out of Calc 2, beyond Calc 2 type of topic. As we try solving for a general first order linear differential equation. So we have to kind of remind ourselves what it means for a differential equation to be a first order. First order, remember, is just highest derivative is the first derivative. And it's a linear differential equation, which is to say that your derivative, y prime, and your y function are not composed with any other functions. Now, there could be other functions that exist, and they could be squared or square rooted or signed or ln or whatever, but the y's and the y primes are not. So, a first order linear differential equation is of this form. Some function times y prime plus another function times y is equal to another function. And what we want to do is that if we have this form, we want to put it in the standard form where you have all the y's and y primes on one side with the y prime by itself, and then you have some other function of x on the other side. And then this form will help us solve for this differential equation using a particular process called, what's it called? Something. Coming. Integrating factor. Wow, that was hard. All right. So what we want to do is we want to look at this form and say the left-hand side of this form kind of almost, if you look at the y prime and the y, it kind of looks like a product rule. It doesn't really, but let's pretend it kind of looks like a product rule and say, derivative of the first times the second plus the first times the derivative of the second. Except there's something missing, right? Obviously. We want to know what's happening with this p of x over here. And so what we're going to do is the process here is to force this thing to look like a product rule. And then we're going to take advantage of some calculus to undo the product rule and then be able to solve for it that way. But first, let's take a look at a couple of simple examples and see if we can turn these into standard form if they aren't already. So first of all, this example, which we already know the solution to, right? What's the solution to this first example here? Is y equals y naught e to the power of what? 5x? Close. Oh, yeah, that's right, 5x. So that's our solution for this, right? You know that, right? We did that last time, separable, blah, blah, blah. It is a separable differential equation, but we can approach this integrating factor technique to solve for it as well. So in order to do that, we want to write it in standard form. So writing it in standard form, what do we need to do? Is it already in standard form? Not quite. It's close, right? What do we need to do? Yeah, just bring the 5x over to the other side. Or 5y. So now it's in standard form. And then the same thing over here. How do you make this into standard form? Second one. What? And divide by x squared. So we got y prime is equal to, plus 1 over x, y is equal to 1 over x squared. Is this still linear? Yeah, it's linear, right? The 1 over x is just, and the 1 over x squared, those are functions of x. And the y itself, or the y prime, are not being raised to any power, so this is still a linear differential equation. All right, so what do we want to do with these types of differential equations? What we want to do is, like I said, we want to make the left-hand side look like a product of something. So for it to look like a product, let's introduce this new function mu, where mu of x times y is going to be the result that we want on the left-hand side, or the derivative of that. So what is mu? If we take the derivative of this mu times y, according to the product rule, it's the derivative, it's the first times the derivative of the second plus the derivative of the first times the second. All right, so that's a derivative of mu times y. And then what we want to do is we want to make it look like the expression that we have. So we're going to want d mu dx to be mu times the p function that we're looking for. Okay? Does that make sense? This process? And so if we solve for mu, because that's what we're doing, we're kind of setting this up to find mu, we're going to get in this expression that needs to be the derivative of mu times dx, or derivative of mu with respect to x. And so you set these two things equal to each other. It's a separable differential equation, isn't it? It's a separable differential equation, and then if you solve for mu, which is what we're going for, we would integrate both sides. So what's the integral of the left-hand side? What? ln of mu is equal to, well, we don't know what p of x is. P of x is going to be different in different problems that we're dealing with. So let's just say the integral of p of x dx. And if we really want to finish solving for mu, what's mu equal to? It's what? Wait, I can't hear you. What's mu equal to? E to the power of. So mu of x is equal to e to the power of the integral of p of x dx. And this is our integrating factor. What that means is that this is the factor, this is the function, the expression that we're going to multiply the equation by, so that we can look at the left-hand side as a product rule and then eventually be able to solve for the problem. Okay, so that's the plan. Let's take a look at these examples that we were looking at earlier. Whoops. And see if we can solve for this. So the first step was the step that we took earlier where we would write it in standard form. And now let's figure out what the integrating factor is. So the integrating factor, according to this, we can do all the steps from scratch, but a lot of times people just kind of refer to this integrating factor. And so if you just remember, memorize, or whatever you want to say, your integrating factor is going to be e raised to the integral of, what's p in this case? -5. So let's keep the negative signs there because that will be important for us, right? Dx. So that's our p. That's your p of x function. And then we're going to get e to the -5x. So that's your integrating factor. So what this is saying is that if I multiply this expression by the integrating factor, and not just multiplying the left-hand side, but we have to multiply the equation to keep it, equal, then the left-hand side should look like a product rule. So let's see if that's actually true. E to the -5x dy dx minus 5e to the -5x times y is equal to 0 times e to the -5x is 0. So now if you look at the left-hand side, first times the derivative of second plus the derivative of first times the second. What's the first function? E to the -5x. What's the second function? Y. Right? So if you can somehow convince yourself that the derivative of this product is equal to that expression right above it. First times the derivative of the second plus the derivative of the first times the second. Yes? Yes. Yes, I think so. Unless there's some tricky true-false question that I throw on the test or something. Any questions so far? Say it again. I don't know. No, because we still have to integrate, right? Because we're solving for y. So now that we got this left-hand side to look like a derivative of something, we're going to integrate both sides. And when we integrate 0, indefinite integral, that's going to be constant. The integral of 0 is a constant. What's the derivative of a constant? 0, right? So we're going antiderivative. It's not a definite integral. It's not going from something to something because then that would be 0. But this is an integral of a constant, an indefinite integral of a constant. So we integrate both sides. And we're the integral of a derivative, according to the fundamental theorem of calculus, is the function itself. And then integral of 0, indefinite integral of 0 is a constant. We can call it y naught, we can call it a, because when we solve for y, it's that constant times e to the positive. Edgar's looking at this kind of funny. Wait, what's wrong? There. So bring the -5, e to the -5x to the other side, it becomes positive 5x, and then here's your solution, which is what we expected from this problem. Because if you did the separable differential equation way of doing this, we separate it, and then we would get the same result. Okay? Questions? So this is a technique. This is an integration technique, solving for differential equations, and just like that chapter in Calc 2 where you learned all kinds of different techniques, right? In Calc 2, you remember you went through doing like volumes of revolution and the work problems and stuff like that. And then at some point, they focused on just techniques of integration. So we're going to learn a bunch of techniques for solving differential equations in this class. And you know, the first one, separable differential equation, is kind of like Calc 2 stuff, but this is the first technique that we're kind of going beyond Calc 2 methods. Yeah. Oh yeah. I mean that's kind of like the section 1.3 that we didn't do in a class, but there's a video there for you. And then we're going to solve for a bunch of those things. Okay. Any questions? Let's try out that second one. So this one is also a first order linear differential equation. And in the process, all you really need to do is identify the p of x, right? So what's p of x in this case? 1 over x. So if we take a look at p of x is 1 over x, we go through that formula. You remember it's e to the integral of p of x. So our mu is equal to e to the integral of p of x dx. And what is the integral of 1 over x? ln x. So mu is equal to e to the ln x. Now, this is technically an indefinite integral, so technically there would be a plus c here. Just like technically there would be a plus c over here, but I'm not going to do it in the class. But if you put a plus c on this integral, and then you follow the work through all the way to the end, you'll see that that plus c will merge into the plus c that you get when you take the integral again later on. And so we don't do a plus c when we find the integrating factor. Okay? So we'll just leave it as e to the ln x, which is equal to what? So mu is just equal to x, so that's our integrating factor. So what we're going to do is we're going to, from here, just multiply this by x. 1 over x times x is just, I'll put a 1 here to be a little bit more explicit, but you don't need to put that 1 there. Anyways, if you look at the left-hand side, it's another product rule, right? It's x times y. So the derivative of x times y is equal to that expression right above it. It's x times derivative of y plus derivative of x, which is 1, times y. And then we look at it as a derivative of a product so that we can, at this point, integrate. And we integrate, that leaves us with x times y on the left side and the antiderivative 1 over x again, ln x. Now we put a plus c. And the plus c, if you would have put a plus c up here, you would also get the plus c down there. Yeah. Yeah, you should. Yes. So we're not factoring. No. What we're doing is we're looking at it as if it was a product rule. And we're going, instead of, the product rule, we take the derivative and then we get two things. This time we're going backwards of a product rule. We're taking the two things and then looking at it and say, hey, this here is a product. Actually, the arrow should be going the other way. So this is actually a product rule, and we're going backwards from a product rule. So we're not factoring. And so when we're looking at this step, after we multiply by the integrating factor, and then we're going to come to this step, what we're doing is we're looking at this and saying this is a product rule from two functions. So the integrating factor forces your left-hand side to look like a product rule of something, and you have to figure out what that something is. Well, no, there's actually a trick to it, because according to the way we found the integrating factor, the product that we're looking for is mu times y. So it's always going to be mu. Your product here is going to be mu times y. And this is mu. When we find mu up here, we find that, and we know that that's going to be the first factor in your product. And then the second factor in your product is always going to be y. Yeah. No, the y doesn't go into integrating factor. You're just looking at the p of x, and the p of x is the number or the function next to the y, not the y. Anything else? Good questions. All right, let's finish this. I think I just have to divide by x. Now, there's a plus c here, so when you divide by x, keep in mind that the plus c also gets a 1 over x. Okay? If it was a constant times plus multiplied or anything else times another constant, then it's just another c. But x is not a constant, so you have to leave it as x. So in this case, our final answer should be 1 over x ln x plus c over x, or you can ln x plus c, the whole thing divided by x, or whatever you want to call it. But this is your final answer. All right? Yeah. Yes, if you divide by a variable with a constant, keep the variable as a variable. When you deal with constants and then you merge with another constant, you could just call that another c. It's just going to be another c. Yeah. All right. Why don't you guys try a problem? Pick a number between 10 and 17. Oh, 21. How are you guys sharp with your trig integrals? Let's do a trig integral. Why you guys moan? I'm gonna do it eventually, anyways. You, you guys are just gonna pretend to try it. I mean, you guys are actually gonna try it, and then we'll go over it. Let us do 21. Did that slip out? And if it gets really hard and we get stuck, it's all Philip's fault. All right, I'll give you a couple minutes to work on your own, and then another couple minutes you can start talking to other people if you get stuck, and then we'll go over it. Uh, okay, how's it going? All right, let's take a look at it. So once you know the antiderivative of secant theta, then this should flow a little bit easier, well, a little bit better. So the integral of secant theta is secant theta plus tangent theta in the ln. And so e to the ln of that is just going to be secant theta plus tangent theta. Now that we have that, we're going to take that expression and multiply every part of this equation on the left and the right side. And so they all got a secant theta plus tangent theta. And the whole point in doing this, and without even thinking about it by now, is that this is a product rule. So this left-hand expression is just a derivative with respect to your independent variable. It's the derivative of the mu function that you found times the y, or the dependent variable, which is r. And that's what you're eventually solving for. And what? Oh, because this is supposed to be mu times. How? No, I would take the derivative of this to check to make sure it's right. Should we check to make sure it's right? It's right. So if you take the derivative of this, you'll have secant theta tangent theta plus derivative of tangent theta secant squared theta Um, it's right. All right, so now that we have that business, we look at the right-hand side, and we're going to integrate this. So I hope to simplify this a little bit, and it looks like they both have a cosine in the denominator. So this would be 1 over cosine, and so the cosine would disappear. That's just 1. And then sine over cosine, the cosine would disappear, and that would just be a sine. Is that right? We need some. I haven't integrated yet. Yeah, I just simplified. And so what we want to do is we want to try to simplify before we integrate. I believe so. You don't know my writing yet? Come on. I should just type this up, huh? All right, maybe we'll do that one day. LaTeX. All right, so let's go on and solve for this. This is the point where we integrate. This is the point where we integrate, and then when we integrate this, it'll just be secant theta plus tan theta times r, and then the integral of this is with respect to theta. So it'll be theta minus cosine theta. Then we throw the plus c in there. Yeah, at this point, I don't know if there's much simplification happening. So that's all we got. And if you want to check, you should take the derivative of this and then put it into this original equation, and we should get a true statement. Yeah. Well, there's certain things you can skip, but you still have to, you need to multiply this right-hand side to make sure that you get the correct right-hand side. So be careful and make sure you don't lose anything when you're skipping steps. Okay? So let me squeeze in the step-by-step process. It makes this into like a little recipe, a little algorithm. When you see a first order linear differential equation, step 1, put it in the standard form. Step 2, from the standard form, find your p of x. That's the factor that's being multiplied by the y term. And then find the integrating factor, and there's a whole formula for that, which isn't really much of a formula. Well, it is a formula. Multiply the standard form by the integrating factor. The left-hand side is going to be a derivative of a product, and the product that we're looking for, we can actually identify that as mu times y. And then integrate both sides so that the left-hand side would be your integrating factor times the dependent variable, mu times y. And then the right-hand side would be whatever the integral is. And then solve for y. In most cases, you should be able to solve for y. And then that's it. So this could couple of these steps could probably be broken down in a couple more steps, but we try to make it compact for you. It's a 4-step process. So let's see if we could do another example. Sorry, I'll get back there in a minute. Whoa, this is a piecewise function. Yeah. All right. Here's an example. This is a fairly straightforward example. There's just a lot of letters here. So just remember which ones are your variables. That's really the only thing you need to focus on. Everything else is going to be constant for us. So we'll treat it like a constant. All right, step by step. Step 1, put the equation in standard form. So looks like there's an L being multiplied with the derivative. So let's just divide everything by L, assuming L is not equal to 0. So it looks like our independent variable is t and our dependent variable is I. And then we find, identify your p of x and find the integrating factor. So our p of x is r divided by L, which is a constant. And then find our integrating factor. So mu of t, just so we remember that our independent variable is t, is going to be e raised to the integral of r over L dt. And the integral of that is just r over L times t. So this is e to the r over L t. That's your integrating factor. So we'll multiply both sides of the standard form by the integrating factor. So we have e to the r over L times t times di dt plus e to the r over L times t times r over L times I is equal to e to the r over L times t times e over L. Okay? So we multiply the standard form by the integrating factor, and then the left-hand side is the derivative of the product. So we want to identify the left-hand side of the equation as a derivative of the product, and the product is going to be the integrating factor times the dependent variable. Okay? So that's the end of step 3. Step 4, we integrate both sides, and then we solve for y. So let's integrate both sides and solve for y. The integral of a derivative is the original function. And the integral of this, e over L is a constant, and then the antiderivative of e to the RL over t is e to the RL over t times, or divided by, or whatever. after you do a u substitution, you get this extra divided by r over L, right? And so you can take the reciprocal so that you can see the L's cancel and all that stuff. All right. So we have E times L, E to the R over L times T. And then the last step is to solve for the independent variable. Oh, there's a plus C here, sorry. Plus C. And so we divide by this thing, we're going to get E, L, and then if we divide this, then that's gone, and then we have a constant over E to the R, L, T. Okay? Am I done? Not quite done. This problem has an initial condition, and the initial condition is used to help us solve for the constant. So we need to continue solving for this constant, and the piece of information that we need is this I sub I of 0 is equal to I naught. That's the initial current. Oh yeah, this is circuit stuff. Anybody taking circuits or something like that? No, whatever. All right, so let's use the initial conditions. When t is equal to 0, I is equal to I sub 0. So we have I sub 0 is equal to E times L plus some constant, and then E to the, well, it doesn't matter what R over L, E to the 0, that's just 1. Yeah. Oh, sorry, I skipped a step here. I divided by this thing. All right. Oh yeah, E over R. Like that? Thank you. Yeah. So it looks like our constant is I sub 0 minus E over R. See if we can put all that together. So we have I of t is equal to E over R plus I sub 0 minus E over R divided by E to the R over L t, which we can somehow rewrite it. I mean, we could put the E to the R over L t as E to the negative R over L t in the numerator. But I don't know if there's much to gain from that. But sometimes people do that so that there's no denominators happening. Okay? I did something wrong again? You got, you put in 0 for t, right? Is that right? Okay, so I think either of these forms would do, and this is should be the final answer. So a lot of times your integrating factor will have some e to something on it, and then when your integrating factor has something like that, and then you multiply it to the other side to solve for y or to solve for the dependent variable, then it usually has an e to the negative something. And so e to the negative something, as t gets larger and larger, what happens to e to the negative 5t? E to the negative 7, e to the negative something t. What happens in your exponential function? It goes to 0. So if you take the limit of this as t goes to 0, then the second term over here with the e to the negative RL over t, or RL times t, goes to 0, and then the only thing that really matters is this e to the r. And so these things that end up going to 0 have a special name for them. And like I said, it's pretty popular that these things happen. So a term that approaches 0 as x goes off to infinity is called a transient term. So it turns out that in this problem and a lot of other problems that we see in the first order differential equations, we have transient terms that end up going to 0. And if you were to graph this, then your function will eventually approach this as the independent variable gets larger, your function will approach e over r, or whatever that term is. If it's a function, then it's a function. Otherwise, it's some constant, and then it has a horizontal asymptote. Okay? Any questions? All right. Yes. No, the whole thing here. Because of e to the negative something t. This is what makes it. This approaches 0, so e to the negative r over lt goes to 0 as t goes off to infinity. And so because of that, that makes anything that you multiply by it will also disappear. As long as there's no t's in it that, to work with. All right. Any questions? Okay, so the best way to really get a handle on this is to practice. So you guys have homework assignments, but then you also, if the homework assignments aren't enough, then you should also, try some other problems in the book. Look at the odd problems and try to do it and check your answers and stuff. But this is pretty mechanical, and just like a lot of the techniques, integration techniques that you learn in Calc 2. There's usually an algorithm where you look through your set of techniques, and I look at a differential equation and say, okay, this is a first order linear differential equation. I know exactly the steps to take. Now these steps over here are suggested steps. I would, if you really want to be thorough, I could probably take a look at step 2 and break that up to 2 steps. Step 3 can be broken up into a couple of steps. Step 4 can be broken up into a couple of steps. And then you would include, in your writing your notes for yourself, you can include, what formulas should be there. So I would suggest that you really take this and you own it by changing things to make it fit with how you learn. If you learn with more steps, then break it up into more smaller steps. If you're fine with this and you think you got a good handle on it, then take the step-by-step process, take this step-by-step process and do a couple of examples to see if it works for you. Okay? But practice, because watching me isn't going to do anything for you. All right.